Hello and welcome to Chapter 5 Practice Problems video. The very first page was one that we did in class and is something that will be talked about through the rest of the video. So for this video we're going to be going through the first couple pages and to make sure I have enough time, these videos probably won't go all 15 minutes in total. For one video they'll probably be a little bit shorter just so I can section them off to make sure I have enough time for everything. So to get us started, the cumulative probability for an entire binomial distribution does not have to sum to 1, and that answer is false. Anytime we're dealing with probability, the total sum is always going to be 1. Part 2 here for true or false is the probability of success. P can change in repeated trials of a binomial distribution, and that is also false. The probability cannot change in a binomial distribution. Next part is we have a multiple choice in scenario. Once again, going with binomial distribution, the probability of P cannot change, and our value of N, the total part that we're dealing with is not going to change. So reading these scenarios, you can see that our probability is either changing or it's non-existent, and then the key part is like which one is the best scenario for a binomial distribution for most acceptable, and that'd be answer number C. Moving along here, we're going to match the following values. So remember, discrete is a very hard number, whereas B is a continuous random variable and C is a non-random variable. When we go through this, I think a better wording of instead of exact weights of newborn babies would just be like weights of newborn babies during a time period, and newborn babies, their weights are always changing. It's going to be continuous. Whereas more shoe sizes of humans, I mean, this probably should maybe say like adult humans, because as kids they're changing, but this is really more of adult humans on average. And that will be our discrete random variable. And then classification, gender classification in the United States will be C as a non-random variable. And that'll give us letter A, or answer A, so B, A, C. Number 3, so in a certain town we have 22% of voters. We want to construct that are in favor of construction of a new hospital. We have a group of 21 voters. Find the variance in numbers who are in favor of the new hospital. So remember, since we're trying to find the variance, our variance is sigma squared, which is equal to n times p times q. So if we have 21 individuals and our p is 0.22 for 22%, our q is 1 minus 0.22, which will give us 0.78. When we do this all out, we'll get a value of 3.6. Now remember, that's voters squared because we're in variance. Our units are squared. Going on, now we want to find the standard deviation for our binomial distribution. So remember, standard deviation is equal to the square root of n times p times q. So we're doing the same thing that we did above, except we're just going to take the square root now of it. So you're going to find your n, which is 503, times p, which is 0.7, times your q. Remember, q is 1 minus p, or the probability of failure, which is 0.3. And then we're going to take the square root of that, and you'll get an answer of 10.28. Number 5, we're finding the mean for a binomial distribution. That's just n times p. So that's 676 times 0.7, and when you multiply those out and get your mean, you're looking at answer B, 473.2. Part C here. So part C, there's a big paragraph and there's a lot of things going on. But you just really need to know, read the very last part. What are you trying to find? You know, any kind of statistics problem, we want to narrow down what is the question asking us. Because then from there, if we know what it's asking us, we can look our formula and see that we need certain values and then go look for those values. So at the very end it says find the mean of the appropriate Poisson distribution, aka, find the mean. Anytime you see find the mean, or if you see anything that says, what is the expected value, those are all mean words that we're trying to find. And our mean is set up the same way for a Poisson distribution as it is for a binomial distribution, which is your mean is going to equal n times p. So we're going to find out how many individuals we're looking at here. And so we know that it kind of says the mean number of cases in this group is that we're looking at 74,090 children, also states it up here. And then we're trying to find that, and then we have to multiply by the probability. So the probability, says right here, the probability is 0.000037. You can put that in scientific notation in your calculator too. You can change it, multiply those two values together, and you get your mean of 2.7. So number 7, after reading the problem, what we're really trying to find is what they're kind of setting up is a confidence interval here. We haven't gone into confidence interval yet, but this is kind of the basics of a confidence interval. And what we're trying to do is we're trying to find a minimum value that is not significantly low, which would be mu minus 2 standard deviation, and a maximum value that's not significantly high, which is mu plus 2 standard deviation. That period should be there, 2 standard deviations. So we have to find a mean. So we have to get a mean, and we know our mean for a binomial distribution is n times p. So we have a mean that we find is 1,205 times our probability of 0.98. Multiply those out, and we get a mean value of 1180.9. Now we need our standard deviation. So remember, standard deviation is the square root of n times p times q. When we do that, we're going to get a value of 4.85. And so now we want to find our significantly high and low means. So we're going to find our low value, which is going to be low, it's going to be mu minus 2 standard deviations. And then our other value is going to be mu plus 2 standard deviations. Well, if our standard deviation is 4.85, if we multiply that by 2, we're going to get 9.7. So we're looking at now mu minus 9.7 and then mu plus 9.7, and our mu value of 1180.9 minus 9.7. That looks like a 2. Let's get that a little bit better, 7. I know I don't have the best handwriting, but we'll be a little better. And then, missing a value here, 0, and then 1180.9 plus 9.7. When we do that out, add those up, we're kind of given this minimum value, and you should get 1171.2 and then a maximum of 1190.6. And this tells us the values that are 2 standard deviations above the mean and 2 standard deviations below the mean. Moving on now to number 8, where we have a survey where 51% of adults are in favor of wearing contact lenses. And now we want to know, if we select 9 individuals, what are the probability of exactly 3 preferred wearing contacts? Assume that each person's preference is independent of the others. So when we're doing this, we have a binomial distribution here. And when we have our binomial function, we're going to take, how many different ways can you choose 3 adults out of 9? So that's where we're going to get our 9C3. How many different ways can you choose these 3 adults out of the 9? Multiply that by our probability, so 0.51 to the x power of 3. Multiply by q, which is our probability of failure, 0.49. Remember, that's 1 minus p to the n minus x power, which is 6. Now remember, if you add the exponents together, you should get the value of n. And then your x value of 3 should be the same for the exponents there. So now we have our binomial problem here, and then when we solve this out, what is the probability, assuming that contact lenses, people prefer wearing contact lenses at 51%, finding 3 adults out of these 9 that prefer it, we'd see that that's 0.154. There's a 15.4% chance of that happening. Moving on, we're going to do just these last couple ones, then we'll pause the video here so we can pick back up on the next one. So here we have just a regular probability table, and you can notice that our probabilities here are changing, right, each time down, and that's what we find for this digital scale and the accuracy of it. So when we're trying to find, so for number 9, find the probability of getting 3 or more scales that fail to weigh accurately among the 6 scales that are tested. So we're just looking at 3 or more, so we're looking at values of 3 or more, and we just add these together and we get b 0.046, right? It doesn't tell us remember, probabilities to be the same throughout a binomial distribution. If they're already giving us the table, they also need to tell us what the probabilities were and then the binomial probabilities below it. Since that's not there, this is just a normal probability, we're adding it up. And then number 10, we're just writing the notation of a binomial distribution. So what is the binomial notation with 7 individuals and a disease probability of 2.4%. So we write that as x is distributed as b, which is binomial distribution, and then we name our parameters. So the parameters are n and then p. N being the number of individuals, so 7, and p being the probability of success, 0.024, which is 2.4%. And that's just how we write the notation of a binomial distribution. Okay, I'm going to stop there, and I will pick back up the next part in the next video, so there's plenty of time to keep going over all of them. See you in the next video.